In the last video, we gave a lot of theorems and proved a few theorems, but just stated a bunch of different results on global asymptotic stability. So now we're going to go back through and give some examples of what we mean by actually applying each of these different theorems, as well as what we mean by some of the concepts that we used in proving them. But anyway, to start, note that we just defined what it meant to be globally attractive and or globally asymptotically stable. Basically, if something is globally attractive, so if you start anywhere in your domain, and here we're going to restrict ourselves to the positive real axis because this is a mathematical biology course and we don't really care about negative numbers of things like rabbits. But yeah, so if something is globally attractive, it means that if you start anywhere on your domain, so if you start, I don't need that much space. So if we have the positive real line, we're going to say that it goes up to some point A, which might be equal to infinity. So it might be the entire positive real line. And then wherever you start, maybe you start, let's say we have some equilibrium. Let's call it x bar. And what we're saying is that wherever we start, you're going to bounce around and eventually reach it. Or you might do some sort of bouncing back and forth before limiting towards that point x bar. Okay? And just in general, if something is continuous, then globally attracting also means globally asymptotically stable, so we don't have to worry about that very much. But let's give an example where this lat fails. So this is where the two concepts of globally attractive and locally stable are different. So this is example 2.7. So we're going to define a map. F, it's going to be on the entire positive real line. And we're going to define it by f of x is equal to 2 if x is between 0 and 2 inclusive, and x minus 1 if x is bigger than 2. Let's give myself some more space. Well, this is an example of something that is globally attractive but not locally stable. So if we draw out what we're doing here, so let's say this is 1, 2, 3, and so on. Let's actually give myself 4, 5, 6, and so on. Okay, so if we start somewhere around here, well, then you're going to go here, and then here, because you're subtracting by 1 each time. You're going to get less than 2, and then you're going to jump back here, all the way to 2. And it's clear that no matter where you start, if you start less than 2, well, you're just going to jump directly to 2 in a single step. And if you start greater than it, then you're going to go back down 1 by 1 until you reach it. Regardless, you obviously are going to limit to 2. So let me write that down. So then for x sub t plus 1 is equal to f of x sub t for all x naught. So no matter where you start on the positive real line, the limit as t goes to infinity of x sub t is equal to 2. So x bar equal to 2 is globally attractive. However, it is not locally stable because you might jump far away. But remember the delta epsilon definition of locally stable, so let epsilon be equal to 1/2. Well, then for 2 is less than x naught is less than 2 plus epsilon. x1 is less than 1 plus epsilon. And x1 minus 2 is greater than 1/2, plus x bar is equal to 2 is not locally stable. Because even if you start really, really close, let me put this in green. Even if you start really, really close to 2, you still have to jump all the way away before you jump back. And so it's not locally stable because you take a moment to go away from the equilibrium. Okay. So, but you'll notice that the reason for that is because this is discontinuous. If if f were a continuous function, you couldn't have this sort of behavior. So now we start on the bulk of the video, bulk of the lecture, which is a bunch of different theorems giving you conditions that allow you to say that a particular equilibrium is globally asymptotically stable. Now, the first thing you should notice is, of course, there can only be one equilibrium that's globally asymptotically stable, because if you had two of them, you can't limit to both of them. Okay, and the very first one is we can prove under pretty restrictive conditions that if f of x is always less than x and greater than 0, then the origin is globally asymptotically stable. And the way you do this is you show that you have, let me give myself a little bit more space here. So basically what we're saying is that on some real line, you have some f of x, and you have some x bar. Let's call this x bar. And their function for every, oh, actually no, we don't even have an x bar here. I don't know why I drew that. X bar here is equal to 0. So we have our 0 here. And then wherever we start, so let's suppose this is x naught. Well, f of x is less than x, so it's going to have to go smaller. And it might be a small step, or it might be a big step, but no matter what it is, it's always going to be smaller. And notice that 0, this is true for any x that's greater than 0, and so it has to keep on going. And 0 is the only fixed point, and so it can't just stop at one of these other points, and so it eventually has to make it all the way down to 0. Okay, so that's not a super interesting example, but basically if your function always gets smaller, well, then you can show that you only have your 0 fixed point is also globally asymptotically stable, because everything eventually makes it there. And this does require continuity, of course. You could imagine scenarios without continuity where this isn't necessarily the case. Okay, so that was an example of a sort of trivial condition. The next theorem, 2.6, is significantly more complicated. So the next theorem, 2.6, so let's actually take some time to parse out what each of these different things means. So first we have x as a continuous function. That's nothing new. And then we also have that f is on or goes from our domain from 0 to a to 0 to a. Also not too interesting. And then, but let's draw out some of the other parts of it. So let me draw out the positive real line again. So we have two different equilibria. So 0, and we're going to call this x bar. Okay? So you have two different equilibria. And we know that for f of x is greater than x, if x is in this region here. So we know that in this region here, things go in this direction. And we know in the other region it goes in this direction. Now note that things might jump past. And so if you have a point here, it might jump past, but then get pushed the other way. But this is the direction in which it will get pushed by applying your f function iteratively. And let's put our a out here, I guess. The last condition is a little bit more complicated, though we sort of tried to illustrate that with some of our drawings. So it's basically, if there is a maximum, then f has to be decreasing past the maximum. If there is a maximum before you reach your equilibrium, then f has to be decreasing all the way after. And just as an aside, if not, if there doesn't exist a maximum, condition 6 holds trivially. And let me show a couple of examples of this. So in this case, here we did no maximum. Actually, let me put this over here. There isn't a maximum, and therefore and you notice that here, what does it mean for f of x to be greater than x? Well, that means it's above. That means it's above the y equals x line. And afterwards, it's below the y equals x line, and so f of x is less than x. So let me actually put that in color. So this is f of x is greater than x, and this here is, oh, I think I reused green, but this is less than x. And you notice the same over here, we have a maximum. Maximum, and f is decreasing afterwards. And of course, you still have it above the line on the left and below the line on the right. Here, we again have no maximum. And we have it's above the line on the left. Sorry, things are mirrored for me. On the left and below the line on the right. Okay, so that was very pictorial and all, but sometimes it's useful to have an actual mathematical example. So let's give one of those. I'll need quite a bit of space for this because we're going to check each of the conditions in turn. So this is example 2.9 in your textbook. And you'll have seen this example before in one of our previous lectures. So if x sub t plus 1 is equal to ax sub t over b plus x sub t, where a is greater than b is greater than 0 on the positive real line, well, then let's check all the conditions. So conditions 1 and 2, f of x is equal to ax over b plus x is continuous on 0, infinity. And you'll note that this is the reason we had to assume that b is greater than 0 and also that x is greater than 0, or greater than or equal to 0. Otherwise, this doesn't hold. And so it's actually super important. This condition is actually super important here, or otherwise we don't have necessarily have continuity. Okay, and what was condition 3? Condition 3, f of 0 is equal to 0, and f of some x bar is equal to x bar. So for condition 3, well, again, we have f of 0 is equal to 0, and that's pretty easy to see. And our f bar we're going to use for x of there. And let's say that x bar is equal to a minus b. So then f of a minus b is equal to a times a minus b over b plus a minus b, which is equal to a minus b. And note that a minus b is greater than 0, so everything holds nicely here. Okay, and we had another couple conditions. We had the greater than and less than conditions. So these are conditions 4 and 5. So note that instead of saying f of x is greater than or less than x, I'm just going to say f of x minus x, and I'm going to see if it's greater than or less than or equal to 0, since that's equivalent, of course. So this is equal to ax over b plus x minus x, which, if you do a little bit of work, is equal to x over b plus x times a minus b minus x. But of course, this is greater than 0 if x is less than a minus b, and less than 0 if x is greater than a minus b. And that you can just see because this thing here is strictly positive. And because that's positive, you only have to look at the term in the brackets. And the last condition is a little bit more painful to check because we need to check to make sure that there are, whether or not there are 2 cycles. So it has an asymptotically stable equilibrium if it has no 2 cycles. So we need to check to see whether or not it does. So condition 6. So, well, the first thing we'll do is f prime of x is equal to, just a moment, f prime of x is equal to the, what was our f of x? Bottom times the derivative of the top. So that's b plus x times a minus top times the derivative of the bottom. So that's ax times 1 over the bottom squared, b plus x squared. And with a little bit of work, this is equal to ab over b plus x squared, which is greater than 0. And this is strictly true, because a and b are both positive, and b plus a squared is also positive. So no maximum in this interval 0 x bar, because things are always getting bigger, and so there's no maximum. Now further, suppose that x is equal to f of x. So we're trying to find 2 cycles now, which is equal to a times ax over b plus x divided by b plus ax times over b plus x, which is equal to a squared x over b squared plus bx plus ax. So what can we conclude? We conclude that x is equal to 0, or b squared plus bx plus ax is equal to a squared. And so this is x times a plus b is equal to a squared minus b squared. Factor out the a plus b. X is equal to a minus b. But of course, these are both our steady states already. So they're already our equilibria, and so we don't have any 2 cycles. So those are our steady states. Therefore, there are no 2 cycles. There are no 2 cycles. So x bar is equal to a minus 1 is a globally asymptotically stable solution. Okay, but sometimes plugging in to solve for a 2 cycle is a little bit painful, depending on what the original equations are. And so some of our other theorems try to change that condition for other ones that are easier to check. Theorem 2.7 is a condition on the first derivative. So if we have a first derivative, that's continuous. If the first derivative plus 1 is not equal to 0. So if the first derivative is not equal to negative 1 for all x in this interval, then there are no 2 cycles of x sub t plus 1 is equal to f of xt on I. So how can we prove this? Suppose there exists a 2 cycle, and we're going to say x naught is equal is less than x1. Then we can just use the mean value theorem for integrals to show that there must exist some c such that 1 plus f prime of c is equal to 0. And this is a contradiction, hence there are no 2 cycles in I. Let's draw a little bit pictorially just so that we have a good sense of what this proof means intuitively. So what we have here is we have some function. We have some function, and between some x naught and some x1, and it does something or another. And if the integral of all that, so all this space, is equal to 0, well, then it So this is some function g of x is equal to 1 plus f prime of x. So we're taking an integral. So if that's equal to 0, if the integral is equal to 0, then it must be equal to 0 at some point. And that's a standard result from calculus. Okay, so moving on from there, let's give another theorem. So these are just, we're trying to give you a toolkit of a bunch of different tools you can use. And so you will have to know these theorems well enough that if I give you a problem that asks, do you prove global asymptotic stability of a particular function, you're able to apply these different tools in your toolkit. So, just a moment. Yeah, so this is, actually, I think it might be a good idea if I give an explicit example of using this condition. Since we're using tools in our toolkit, let's go ahead and give an explicit example of this one as well. So let's see, let's call this I don't know if this has an example number. Let me double check to see if the book has an example number for this. This is theorem 2.7. Yeah, this is example 2.10 in your textbook. So let's suppose that we have x sub t plus 1 is equal to ax sub t over b plus x sub t to the kth power. And we're going to have a, b, and k are greater than 0, and x naught is greater than 0. Okay, so how do we apply this tool? Well, we know that f of x is equal to ax over b plus x to the k. Therefore, 1 plus f prime of x is equal to 1 plus, I'm not going to go through the full computation, but this is something that's pretty easy to check. 1a times b plus x to the k times 1 minus k over b plus x to the k squared. And so one thing that's pretty easy to notice is if k is less than or equal to 1, then 1 plus f prime of x is greater than 0 for all x greater than 0, so no 2 cycles. Okay, and that makes it easier to, so instead of having to actually check f of x is equal to x, you can just apply this derivative test. And so try not to get confused because we're using derivatives for all sorts of things, but this is another derivative test you can use to check to see if there are 2 cycles. Okay, well, let's moving on, and let's give you some more tools that you can use. So this one here is basically, instead of having this super long list of conditions up here, we just have a few conditions. So again, we're going to start out being continuous, and x bar has to be in interval 0a. And what we're going to do is, this proof is really analogous to the proof of theorem 2.6. So 2.5. So in 2.5, everything constantly went down, and so you eventually hit 0. In 2.9, wait, which one am I on? So yeah, sorry, 2.8. What is going to happen is you're going to keep on going down from both sides. So I'm not going to walk through the entire proof, but just a sketch of the basic idea is that if we have some x bar here, this is 0 here. Here, what we're saying is that everything below x bar goes up and might go in bigger jumps and smaller jumps, but it can't actually get past x bar, and everything over here as well. And so because so the additional condition that we have here is that it's still less than x bar, or it's still greater than x bar. And that condition allows us to say that x bar is then automatically a globally asymptotically stable solution because everything's going to it in both directions, and you know that you only have one fixed point, one positive fixed point. 0 is also a fixed point, but we don't really care about that one as much. Okay, and let's see. Let's go ahead and give an example of this one as well. So let's give this an example. of using this one. So let's suppose that we have x sub t plus 1 is equal to ax sub t over b plus x sub t again, which is equal to f of x sub t, and a is greater than b is greater than 0. Well, we know that x bar is equal to a minus b, and we know that ax over bx b plus x minus x is equal to, so I'm not going to work this out, but it's x over b plus x times a minus b minus x, which is greater than 0 if 0 is less than x less than a minus b, and less than 0 if x is greater than a minus b. So, plugging in a minus b, well, we know that ax over b plus x minus a minus b is equal to, if you plug all this in, this will be ax minus ab minus ax plus b squared plus bx over b plus x, which is equal to b over b plus x times x minus a minus b, which is less than 0 if 0 is less than x is less than a minus b, and greater than 0 if x is greater than a minus b. Okay, and what were we doing there? We were just checking each of these two conditions, where depending on where you start, you either end up going upwards or going downwards. And so here what we're saying is that if we yeah, and so that's basically what we just showed there. And then, therefore, so by theorem 2.8, x bar is equal to a minus b is globally asymptotically stable. Okay, and for our final theorem, we gave a slight modification. Instead of talking about 2 cycles, which we did a lot earlier, we can replace the 2-cycle condition with this condition on f of x is greater than x. Let's just give one more example. We're not actually going to make use of the 2-cycle condition in this particular case. Instead, we're just going to check all the conditions 1 through 5 to show that it's globally asymptotically stable. And we're going to give another example of that. So this is example 2.12. So if we have x sub t plus 1 is equal to 2x sub t e to the minus r x sub t is equal to f of x sub t, of course, and r is greater than 0. Then we have 2 equilibria at 0, and x bar is equal to natural log of 2 over r. And we can check conditions 1 through 5 are satisfied. And that's pretty mechanical, so I'm not going to do that. But checking whether or not there is a global maximum takes a little bit more work, so let's do that. So we have f of x is equal to 2x e to the minus rx, so f prime of x is equal to 2e to the minus rx minus 2rx e to the minus rx by the product rule. And so f prime of x is equal to 2 times 1 minus rx times e to the minus rx. So in order to find maximums, well, clearly any maximum on that open interval is going to have first derivative equal to 0, so it's going to have to be a local maximum. So f prime of x of m is equal to 0 is equal, so setting that equal to 0, 1 minus rx sub m e to the minus rx sub m, which implies that x sub m is equal to 1 over r is a local maximum. But the fact that it's a maximum instead of a minimum is something you'd have to check, but we're not going to do it right now. But it doesn't actually matter because 1 over r is greater than natural log of 2 over r, since 1 is greater than natural log of 2. So f has no max. In this interval, thus x bar is globally asymptotically stable. Okay, and there are more examples in the book as well as in your breakout session if you need more practice. This is obviously one of those things where there are a lot of different rules that you need to remember. Basically, there are lots of tools in your toolkit if you're actually going to prove that something is globally asymptotically stable. And it is a little bit more complicated than proving if something's just locally asymptotically stable. So thank you very much, and I will see you in the next video.